Hi everyone, thanks for being here, and thanks to the organisers for inviting me and for arranging this very interesting conference. So I guess we're all here because we believe that in one way or another there's something not quite right about the way people usually think about quantum mechanics. And that's not really terribly surprising because, despite our best intentions, science is never a perfectly rational process, and thus there are likely to be elements, even in our best theories, that are there not as the end point of a process of evidence-based reasoning, but rather more as a result of historical accident. And furthermore, we know that it's often a good way of achieving theoretical progress to identify and eliminate these sorts of anachronisms. So witness the Galilean revolution, the Copernican revolution, arising from removing the assumption that the world must be, the universe must center on the Earth, and the first Einsteinian revolution arising from getting rid of the assumption that simultaneity must be absolute. So I take it to be a worthwhile project to consider which elements of our current thinking about quantum theory might likewise be anachronisms and where we might get to if we try to eliminate them. So that's what I want to do in this talk. I want to identify two elements of our thinking about quantum mechanics that I think are likely candidates to be this sort of anachronism. In each case, I want to say a bit about the historical context of these assumptions in the hopes of convincing you that they might feature in our thinking for the wrong sorts of reasons. I then want to put them a bit in the context of some results of modern physics, and then in each case I want to try and convince you that these aren't just harmless assumptions, they are having a significant effect on the way we do physics, and they're holding back theoretical progress. So without further ado, the first anachronism I want to discuss is what I refer to as temporal locality. So at this conference we've heard a fair amount about spatial locality, and whatever your personal view is on the validity of spatial non-locality, it certainly seems true that since the advent of Bell's theorem, the physics community as a whole has no longer takes spatial locality for granted in the same way that we used to before Bell's theorem. But there hasn't been a similar sort of change in our way of thinking when it comes to what one might refer to as temporal locality, by which I mean in loose terms, that the result of a measurement made at a given time must depend on the state of the world at that time. So we can make that definition a bit more formal by using the language of factorizability that features in the definition of spatial locality. And for those who like formal definitions, I've done that on this slide. But I should note that the vagueness here is, in a sense, deliberate because there are a number of concepts kind of floating around in modern physics which might reasonably be subsumed under the heading of temporal locality. I think that's best illustrated in a kind of contrastive way by describing some ways in which physics might possibly fail to be temporally local. So, for example, we might have a world in which the laws of nature are non-Markovian. So we do have a state evolving forwards in time, but the results of a measurement made at a given time might depend on facts about the past which aren't recorded in the present state. Or alternatively, we've heard a lot this morning about retrocausality. So the results of measurements made at a given time might depend not only about facts about the past as recorded in the present state, but also in some way on facts about the future. And finally, the world might be atemporal, meaning that rather than having a state which starts at the beginning and evolves forward in time, we have a universe which is solved kind of all at once externally, in the same sort of way as the rules of a game of Sudoku apply to the whole grid at once, rather than starting at the left and evolving towards the right. So my discussion in this talk is mainly going to be general enough to cover all of these possibilities, although I may at times betray a prejudice in favour of the third atemporal view. So there are obvious kind of practical and psychological reasons for our preference for temporal locality. We ourselves are obviously spatially and temporally local agents, and it's natural for us to imagine that the laws of nature must be subject to similar constraints. Also, we're obviously often in situations where we know facts about the present state of the world and we want to make inferences about the future from that. And therefore, it's relevant to our practical interests to develop laws which act in a temporally local way. There's also a natural intuitive tendency to think of the present as being somehow specially privileged, and that way of thinking also inclines us to think in a temporally local way in our laws of physics. But perhaps more insidiously, there's also an element of temporal locality which is really built into the structure of the way we think about what constitutes a reasonable scientific theory. And that's because it's more or less compulsory these days to present a scientific theory by describing its kinematics and its dynamics. And there are more broad definitions of this distinction that have been made, but usually when physicists use these terms, what they mean is that the kinematics are a set of states and the dynamics are a set of laws by which those states evolve. And because a state is, in essence, simply that which carries information about the past forwards into the future, presenting a theory in this sort of framework essentially rules out temporal non-locality by fiat, by demanding that all dependence on the past must be mediated via that state. And so Speckens has an interesting essay on this topic where he points out that we can always respond to new piece of empirical evidence by choosing to alter either the kinematics or the dynamics. He argues that therefore this distinction doesn't have any empirical content and we shouldn't be realists about it. To a philosopher's ear, that argument is a bit worrying because it's very similar to the various Quinean moves where Quine points out that basically any distinction in science has that feature. We can always choose to keep something constant within our theories and respond to new empirical evidence by altering other elements of the theory, and therefore theories have content only as wholes, not as individual statements. And so it would seem, therefore, that if we applied Speckens' epistemic criterion consistently, we would end up with a kind of general anti-realism about all theoretical distinctions whatsoever. I want to avoid that, so I prefer to interpret Speckens' point as saying that this distinction between kinematics and dynamics is really a distinction just like any other distinction we might make within a theory. It's a hypothesis, and it should be evaluated as a part of some broader theory. It shouldn't be presupposed as a condition for any reasonable scientific theory as we currently treat it. And it's that presupposition which has funneled our thinking towards temporally local theories, because we are kind of prevented from the very start from even describing theories which don't have that temporally local feature. So we can see then that it's quite easy to come up with explanations for why our theories should have this feature of temporal locality in terms of psychological and historical factors. But none of those explanations are really epistemic justifications for believing that the world actually is temporally local. And I think it's a fairly reasonable epistemic principle that when we can easily explain psychologically why we have a belief, but cannot easily provide an epistemic justification for it, we should have some serious questions about the epistemic rationality of that belief. Another time-honoured way of testing for epistemic rationality is to consider the consistency between a given belief and various other beliefs that we may have better justifications for. And again, on that front, temporal locality seems to be in some sort of trouble. And that's because, as you may have noticed several slides ago, the definition of temporal locality requires us to refer to the state of the world at a given time. And of course, within special relativity, the state of the world at a given time isn't even a well-defined concept. It's not a single category that we can easily delineate, and therefore it's tempting to say that special relativity and temporal locality are just immediately inconsistent. There is a caveat, however, because if you also assume spatial locality, it then follows that the result of a measurement can depend only on the state of the world at the space-time location of the measurement. And of course, the state of the world at a single space-time point is well defined even within special relativity. So if you want to keep both spatial and temporal locality, you're probably all right. But if you believe in special relativity and you're also willing to take seriously the possibility that the world might be spatially non-local, you should probably also be willing to take seriously the possibility that the world might also be temporally non-local. And that gives you a way to have this spatial non-locality without violating Lorentz invariance. The picture, I think, is even clearer within general relativity because, of course, in general relativity, a solution to Einstein's field equations isn't a state of the world at a given time. It's an entire history of a universe. And so kind of a naive interpretation of that formalism would seem to lead us directly towards the kind of atemporal picture that I talked about earlier and that Ken also mentioned. So again, there's a caveat because there do exist initial value formulations of general relativity. Essentially what one does there is we take the field equations of general relativity and we split them into two parts. And so one set becomes a set of constraint equations which must be satisfied by the initial state of the universe. The remaining set becomes the dynamical equations by which that state evolves forward in time. So it is, formally speaking, possible to put general relativity in a kind of temporally local framework. However, what we lose in that picture is the kind of intuitive idea idea that underlies temporal locality of the world as something like a computer which takes in an initial state, acts on it, evolves forward, and produces a final state as output. And that's because it's crucial to this formulation that the constraint equations must be preserved under the evolution equations, and so we can no longer regard the initial state as being independent of the evolution equations in the traditional sort of way. And indeed, there's a sense in which the state of the universe at the start of time has to depend on the state at later times, and so we have some kind of temporal locality or retrocausality being kind of smuggled in through the back door. I will be quick here because Ken has happily covered this for me already, but essentially one might ask, well, if we can do that with general relativity, are there also temporally non-local formulations of other types of theory? And indeed, we have Lagrangian formulations of both classical physics and quantum physics, where we consider, describe how things behave, not by starting at the beginning and evolving forward, but rather by calculating actions, which are, of course, properties of entire histories, not of states at times. And so, as Ken said, it's usual to regard the Newtonian kinematics dynamics picture as a literal description of the world, and to treat the Lagrangian schema as just an ingenious calculational tool, but there doesn't seem to be any very good reason for this choice other than our pre-existing prejudice in favour of temporal locality. Okay, so at this point you may say, well, this is all very well, but does it really matter? Because while some physicists might perhaps be prepared to fight to the death in defence of temporal locality, I imagine that many physicists would simply treat it as a harmless simplification. I, however, want to argue that it is very far from harmless. And that is because, in particular, in the quantum foundations community, it's very common to produce results within what we heard about on the first day and what's known as the ontological models framework. And in the ontological models framework, we assume that the world has a set of underlying states, and we take it that the results of a measurement must depend only on that underlying state. And so I've given here an incomplete list of important results in quantum foundations that are derived within that framework. So obviously the ontological models framework kind of builds in temporal locality in the same sort of way as the kinematics and dynamics distinction does. But furthermore, the temporal locality is really the founding principle of the whole approach, because the very project of constructing an ontological model is all about trying to understand what information must be contained within that ontological state if we are to reproduce the quantitative results of quantum mechanics. So, for example, we heard earlier about the PBR theorem, which is often glossed as proving once and for all that the quantum state cannot be epistemic. But what the PBR theorem really does is it says that this ontological state must contain all the same information as the quantum state if we are to reproduce quantum mechanics. And that's because if that were not the case, one could come up with a set of preparations and a measurement such that we would sometimes get results that contradict quantum mechanics, essentially because, as PBR puts it, this measuring device would not be able to tell which one of the four preparations was used. But of course that conclusion doesn't follow if we get rid of temporal locality, because in that case the measuring device can always just look back and see which preparation was used. So the PBR theorem immediately takes on a very different meaning if we get rid of the assumption of temporal locality. And I would argue that all of these results and similar results within the field of quantum foundations likewise must be understood very differently if you get rid of the assumption of temporal locality. So the whole landscape of quantum foundations really changes a great deal if you discard that assumption. Furthermore, as I understand them, most of the mainstream interpretations of quantum mechanics are explicitly temporally local in their approach. That suggests there's probably quite a large space of other types of interpretations that haven't yet been well explored, which would be temporally non-local, and we might make a great deal of progress if we start paying more attention to those interpretations. Okay, since time is marching on, not intended ironically, I'm going to have to move on to my second anachronism, which is objective chance. Of course, there's a long history in philosophy of distinguishing between what's known as objective chance and subjective probabilities. So that distinction has been made in many different ways throughout the history of philosophy and is still the subject of active debate. And therefore, in order to be clear and simple in this talk, I'm just going to stipulate how I intend to use that terminology, and I won't engage further with debates over the meaning of those words. So I am going to mean by objective chance fundamental and irreducible probabilities, particularly those that appear in fundamentally indeterministic laws of nature. And I particularly have in mind interpretations of those probabilities where they're regarded as being something like propensities, as in the propensity interpretation of probability. I will refer to, by subjective probability, all other types of probability, including things like relative frequency, ensemble averages, ignorance probabilities, and patterns, and emergent patterns in higher level systems. So, of course, the reason this distinction is important for our purposes is that quantum probabilities are at least on the usual way of thinking about quantum mechanics, on the textbook account, and in many important interpretations of quantum mechanics, such as the spontaneous collapse models. In all of these pictures, quantum probabilities are regarded as objective chances. Now that in itself ought to worry us, because it's famously very difficult to give an acceptable account of what objective chances might actually be. And indeed, luminaries ranging from David Lewis to David Deutsch have raised serious questions about the meaningfulness of this notion of objective chance. But I want to focus on a more historical question here, by noting that according to our best current theories, it does seem that quantum probabilities seem to be the only real objective chances in the sense which I've used that term, so in this particularly strong sense. None of our other theories require us to postulate fundamental and irreducible probabilities. It's only quantum mechanics that does that. And I want to stop for a moment to consider how extraordinary that is, because the thing is that this concept of objective chance has been around a lot longer than quantum mechanics. So probability as a sort of formal mathematical field arose in the 16th and 17th century with the work of Cardano, Pascal, and Fermat. And right from the very start, it was always a kind of a dual notion. This idea of objective versus subjective probability has been floating around at least since the time of Laplace, who has this essay where he writes about the unknown inequalities which may exist amongst chances which are supposed to be equal. So he's there making a contrast between the subjective and the objective notion of probability. And for a more detailed account of this sort of duality in the notion of probability, I would refer you to Hacking's book. The propensity theory of probability specifically is much younger than that. So the explicit propensity theory of probability was put forward by Popper in the 50s. But again, the idea of propensity-like chances have been around much longer than that. So for example, in 1910, we find Pierce writing that what a probability means is that when we roll a dice has a certain would-be, which is a property quite analogous to any habit that a man might have. So the take-home is that this idea of objective chance is much older than quantum mechanics. It's been around. It was well known, and people were thinking about chances in this way long before the founding experiments of quantum mechanics. Sorry. No, not yet. So the reason this is problematic is that we know from decoherence that quantum probabilities are effectively suppressed, which means that in our everyday lives we don't have experiences we don't experience quantum probabilities directly. We can't observe any events which are probabilistic in that quantum sense. And that means that the story we're apparently required to accept is that our ancestors came up with this concept of objective chance, which turned out to apply, in fact, perfectly to quantum probabilities, and moreover to describe only quantum probabilities and nothing else. They came up with this concept without ever having any experience of objective chance. They came up with this concept without ever having had any experiences of what we now understand to be objective chance. And that seems a very bizarre thing to believe. It seems a very problematic course of events. For me, what seems much more plausible is to say that what happened was that this nebulous idea of objective chance was kind of floating around in people's consciousness before quantum mechanics came along. Then quantum mechanics did come along, people had these probabilities, they weren't sure what to do with them, they couldn't find an account of them, which they couldn't reduce them to anything in the usual kind of way that we were used to doing with subjective probabilities. So they attached this label of objective chances to them in order to give a semblance of understanding what was going on. But in fact, we didn't really get any greater understanding from that. We just translated a mistake that had arisen in the foundations of probability directly into a mistake into the foundations of physics. So one response that you might make to this concern, and this is indeed the response that was made by David Wallace, they're all called David, when I posed this question in a seminar last year, is that, well, perhaps we can use Kripke's view on a posteriori necessity. We can say it's just a necessary truth that objective probability is quantum probability, in the same way that water just is H2O, even though the concept of water was formed long before we knew of its molecular constitution. I would argue, however, that the cases are quite disanalogous. The concept of water was formed via experience of actual water. People were actually having experiences of H2O, and that's why water is H2O, even though they didn't have that concept at the time. On the other hand, our ancestors came up with this idea of objective chance without ever having had any experience of what we now take to be objective chance. There was no direct causal link between objective chances as we now understand them and the formation of the concept of objective chance. So the fact that they nonetheless managed to come up with this supposedly correct concept seems nothing short of a miracle. Indeed, I would suggest that a Kripke analysis would tend to lead to the opposite conclusion. If you subscribe to a Kripke-like causal theory of meaning, I would say you should probably believe that a situation in which a concept is invented prior to the discovery of its referent is not only very unlikely, but in fact impossible. So we seem to have a problematic epistemic situation here. At this point, I should mention that there are a number of no-go theorems which are frequently raised when people try to explain why quantum mechanics supposedly has to be probabilistic. So Bell's theorem is sometimes raised in this context, but I think we've all established well enough by now that subject to the various assumptions, what Bell's theorem should be taken to mean is that it rules out not determinism, but rather local realism. The Cauchy-Specker theorem is also relevant. So the Cauchy-Specker theorem tells us that there exist sets of quantum measurements such that if you try to build a deterministic model, you will end up having to say that given a particular outcome which can occur in two different measurements, if you make measurement 1, you are certain to get that outcome, but if you make measurement 2, you're certain not to get that outcome. Now that's clearly a problem if you want to make a deterministic model in which outcomes of measurements are in one-to-one correspondence with underlying properties that quantum systems must deterministically have or not have. But there's no obvious reason why a deterministic theory would need to have that kind of structure, and I think therefore the best take-home from that theorem is just that we should be less literal about our mathematics. Likewise, the Renner-Kolbeck theorem says that there's no predictive extension of quantum mechanics that can have greater predictive power than quantum mechanics itself. But the assumption that that's based on is that the extension of quantum mechanics would have predictive power in a practical sense. That is, we would be able to observe these hidden variables and use them in prediction. That doesn't rule out theories where the hidden variables that extend quantum mechanics and make it deterministic are either hidden, or perhaps they're just global constraints of the type we talked about earlier, in which case they wouldn't be observable by observers localized within the universe, and they therefore wouldn't be able to be used in prediction. So none of these theorems really mean that we have to abandon deterministic views altogether. So again, does any of this matter? Well, the reason it matters is that because the concept of objective chance was already around before quantum mechanics was introduced and interpreted, the people who invoke interpretations which use objective chance were never really asked to explain what they meant by that. It's kind of taken for granted that the notion of objective chance is meaningful, that we all know what it means, and so it wasn't subjected to the kind of critical scrutiny that it would have received had it been introduced at the time as a brand new concept. I think that's a problem. I think that people who want to put forward theories which involve objective chance should be required to provide an account of what they mean by that. And until such an account is forthcoming, we ought to have a strong preference in favour of theories which don't require objective chances. And And so finally, I want to just bring some of those things together. There's a reason why I've tried to rush through both of these anachronisms in one talk rather than focusing on one of them, and that's that I think they're connected, and in particular, I think as soon as you abandon temporal locality, it becomes very natural to also abandon objective chance. So first of all, moving to a temporally non-local picture immediately gives us a whole set of new variables which might well give us a way to turn the probabilistic theory into a deterministic one. So going back to my favorite analogy, a game of Sudoku will look probabilistic if you start at the left and try to read from the right and try to predict what's coming next from what you've seen so far. But of course, if you can see the whole thing at once, and if the game has been set up properly to start with, you'll be able to see that there's a unique solution. So in that sense, the game is in fact deterministic, even though to a local observer watching from left to right, it will look probabilistic. So the thought is that the world, our world might be deterministic in that same global sense, even though it is probabilistic from our local point of view. Second of all, there's a question about whether, in that sort of atemporal global theory, would probabilities even make sense? I mean, I said they don't make sense even on a small scale, but things get worse if you try to apply objective chances to the whole universe, because if you, like me, are not keen on the idea of there being loads of other universes, the universe is only going to be given to us once. There's no ensemble to which those probabilities can be referred. They seem even less meaningful in that context than they did in our everyday lives. And finally, I would argue that part of the reason why we've found it necessary to invoke these objective chances is our preference for temporal locality. Because we see, when we consider our observations, we see this kind of global coordination across time. We see patterns in the way things behave across time. And when because we're realists, we want to provide an explanation for that. If we find we can't straightforwardly do that in terms of hidden variables or common causes, it seems like our only option is to invoke some kind of objective chances which are responsible for those observed patterns. But if you abandon temporal locality, you don't need objective chances because the coordination can be explained directly by a global coordination that arises from global laws applied to the whole of history all at once. There's just no need for us to invoke these objective chances. So by getting rid of that first anachronism, we can also get rid of objective chance and thus conveniently also solve a irritating philosophical problem that's been hanging around for quite some time. So on that appealing prospect, I guess I must finish, and we can move to questions if there are any questions.